Good morning, my dear students. Now we move to the module Ionic Equilibrium, where we have to see about the acids, pH values, buffers, and hydrolysis of salt. So we have to see what are acids and bases. Moving to the concept of acids and bases, we have to talk with three concepts of acids and bases. And the first concept is the Arrhenius concept of acid and bases. As per this concept, an acid is a compound or a substance which could give or donate H plus ion in water or aqueous solutions. That means any substance which could donate H plus ion in aqueous solutions are called acids. Now we could say HCl is an acid. Why? Because when we consider HCl in water decomposed to give H plus ions and Cl minus ions. Here HCl is giving you H plus ion or proton, and hence we could say it is an acid. As per Arrhenius concept, bases are substance which could give you OH minus ion or hydroxyl ion in water. That is why we consider NaOH as a base, because it gives you OH minus ions when dissolved in water. That is, NaOH when dissolved in water will give you OH minus ion. And as per Arrhenius concept, NaOH is a base because it gives you OH minus ions. So, according to Arrhenius concept of acids and bases, any substance which donate H plus ion are called acids, and any substance which donate OH minus ion are generally termed as bases. The second concept of acids and bases is Lowry-Bronsted concept. As per this concept, any substance which donate H plus ion is an acid, while any substance which accept H plus ion is a base. See, in Arrhenius concept, any substance which donate OH minus ion is a base, but as per Lowry-Bronsted concept of acid and bases, any substance that could accept an H plus ion or a proton is termed as a base. Now see the example. HCl reacting with H2O to form H3O plus ion and Cl minus ion. H3O plus ion, which is the hydronium ion, and Cl minus ion, which is the chloride ion. When we look this particular reaction, HCl is an acid as per Lowry-Bronsted concept because it donates its H plus ion to form Cl minus ion. So, HCl is donating or losing H plus ion, and hence it is an acid. Moving to water, H2O accepts H plus ion donated by HCl. So, any substance which could accept H plus ion is a base. That is, H2O is accepting H plus ion to form H3O plus ion or hydronium ion. Hence, we could say H2O is a base and HCl is an acid. Now, consider this example. NH3, that is ammonia, combines with water H2O to form NH4 plus ion, that is ammonium ion, and OH minus ion, that is hydroxyl ion. Now we see this reaction in the forward direction, or if we analyze the forward reaction, NH3 is accepting H plus ion from H2O. So we could say any substance which accepts H plus ion is a base. That means here NH3 is accepting H plus ion and hence it is a base. So NH4 plus is formed. Now moving to water, H2O, H2O is donating its H plus ion and getting converted to OH minus ion. Hence we could say H2O is donating H plus ion. As per Lowry-Bronsted concept, any substance which donate H plus is an acid. Hence H2O is an acid. So we could say in the forward reaction, NH3 is the base and H2O is the acid. Now look to the backward reaction. When we look to the backward reaction or we analyze the backward reaction, NH4 plus, that is ammonium ion, is losing H plus ion and converted to ammonia. That means NH4 plus is donating H plus ion. Any substance which donate H plus ion is an acid. Hence NH4 is an acid. NH4 plus is an acid. OH minus is accepting H plus ion from NH4 plus. So when we see the backward reaction, the hydroxyl ion accept H plus ion and converting to water. Any substance which accept H plus ion is a base. Hence OH minus is the base. So we could say in the forward reaction, NH3 is the base and H2O is the acid. Considering the backward reaction, NH4 plus is the acid and OH minus is the base. And when we analyze this particular reaction, NH4 plus is formed from the base NH3. NH4 plus is an acid which is formed from the base NH3. Hence we could say NH4 plus is the conjugate acid of the base NH3. NH4 plus is the conjugate acid of the base NH3. That means we are bringing a concept conjugate acid and base. In this particular reaction, NH3 and NH4 plus are conjugate base acid pair because NH4 plus is formed from the base NH3. Hence, NH3 and NH4 plus are conjugate base and acid pair. Similarly, when we analyze H2O and OH minus ion, OH minus is a base which is formed from the acid H2O. Hence, OH minus is the conjugate base of the acid H2O. So, in this particular reaction, NH3 and NH4 plus are conjugate base acid pair and H2O and OH minus are conjugate acid base pair. This I have explained earlier. See, NH3 which is a base combining with water which is an acid to form NH4 plus and OH minus. So, NH3 and NH4 plus are base conjugate acid pair and water and OH minus are acid conjugate pair. Now see here, for NH3 the conjugate acid is NH4 plus. For OH minus it is HOH. Similarly for H2O it is H3O plus and this is bicarbonate ion, it is carbonate ion which is bicarbonate ion. Take down. Now consider this example. HF, hydrogen fluoride, combines with water to form F minus ion and H3O plus ion. F minus ion is fluoride ion and H3O plus is hydronium ion. When we look into the forward reaction, HF, which is an acid, donate H plus ion to form H3O plus. That means HF is acting as an acid which donate H plus ion to form F minus ion. When we look back the reaction, backward reaction, F minus accept or gain H plus ion to form HF. Any substance which gain H plus ion or proton is a base. So, F minus and HF are the acid conjugate base pair. Moving to water molecule, H2O accept H plus ion, hence it is a base. And hence we are getting H3O plus ion. H3O plus ion is losing or releasing or donating H plus ion to form H2O, water molecule. Hence, it is an acid which donate H plus ion. So, in this particular reaction, HF and F minus are conjugate acid base pair and H2O and H3O plus are conjugate base acid pair. Now consider these examples. First example, HCl combining with ammonia to form NH4 plus and Cl minus. HCl is acting as an acid in the forward reaction. Why? Because it is donating H plus ion to form Cl minus. While NH3 is accepting an H plus from HCl to form NH4 plus ion. Hence, it is a NH3 is a base. So, we could say in the forward reaction, HCl is an acid while NH3 is a base. Considering the backward reaction, when we consider the backward reaction, NH4 plus is acting as an acid. Why? Because it is losing H plus ion or donating H plus ion to Cl minus to form HCl. Hence, NH4 plus act as an acid. See here, Cl minus is accepting H plus. We know, according to Lowry-Bronsted concept, any substance which accepts H plus ion is a base. Hence, Cl minus is a base. Looking to this particular reaction, we could say HCl and Cl minus are conjugate acid-base pair, while NH3 and NH4 plus are conjugate base-acid pair. Similar the reaction NH4 plus and OH minus, HNO3, H2O, H2SO4, H2O. In all these reactions, the substance which donate H plus ion is acting as an acid, while any substance which accept H plus ion is a base. So, in the second reaction, NH4 plus is donating H plus ion, hence it is an acid, while OH minus is accepting an H plus ion, hence it is a base. So, here NH4 plus is the acid and NH3 is the base formed from NH4 plus. Hence, NH4 plus and NH3 are conjugate acid base. So, we could say any substance which is formed after donating H plus ion could be considered as a conjugate base. Any substance which accepts H plus ion and forms a acid, it is a conjugate acid. Now we move to the third concept of acids and bases, that is Lewis concept of acid and bases or Lewis concept of acids and bases. As per this concept, any substance which could accept a pair of electrons is considered as a Lewis acid. If a compound could accept a pair of electrons from any other compound, then it is a Lewis or Lewis acid. While any substance, if it donates an electron pair, it is considered as a Lewis base. See, for example, when we consider NH3, NH3 is having a lone pair of electron here. This lone pair of electron could be donated to the boron in BF3, where BF3 is a electron deficient compound. Hence, NH3 is acting as a Lewis base because NH3, which contains a lone pair, is donated to BF3, which is an electron deficient compound. Hence, we could say NH3 is a Lewis base. And BF3 accepted the lone pair of electron from NH3. So we could say BF3 is a Lewis acid. So as per this concept, any substance which could donate a pair of electrons is called a Lewis base, while any substance which could accept a pair of electrons is a Lewis acid. That means electron pair acceptors are Lewis acid and electron pair donors are Lewis base. Or we could say electron deficient compounds are Lewis acids, while compounds having lone pairs which are able to donate are called Lewis base. See some more examples here. NH3, H2O, they contains lone pair of electrons. Hence, they act as Lewis base. While BF3, AlCl3, CH3CO+, these compounds or these ions does not have electron pairs or they are ready to accept electron pairs. Hence, they are termed as Lewis acid or Lewis acid. So we have discussed the concepts of acids and we have discussed three concepts of acids. They are Arrhenius concept of acid and bases, Lowry-Bronsted concept of acids and bases, and finally Lewis acid and bases. Now we move to another topic, that is ionic product of water. We know water molecule can act as a base as well as an acid. That means it is an amphoteric substance. Substances which could act as an acid as well as a base is called amphoteric substance. So, water molecule could act as acid as well as base. Consider this reaction. In this particular reaction, I have two molecules of water. Out of these two molecules, one molecule of water accepts H plus ion from the second molecule of water to form H3O plus ion. Hence, the first molecule is acting as a base because it is accepting H plus ion, while the second molecule is acting as an acid. By donating H plus ion, it becomes OH minus ion. This reaction could be simplified in another way. See this particular reaction. One molecule of water is decomposing to form H plus ions and OH minus ion. When we consider these two reactions, we could say the molar concentration of H3O plus ion is equal to the molar concentration of OH minus ion. Why? Because one molecule of H2O accepts H plus ion to form H3O plus ion. And the second molecule of water is losing H plus ion to form OH minus ion. Hence, the molar concentration of H3O plus ion, that is hydronium ion, is equal to the molar concentration of OH minus ion, that is the hydroxyl ion. Moving to this particular reaction, the molar concentration of H plus ion is equal to the molar concentration of OH minus ion. So we could say water could act as an acid as well as a base. Studying this, they proposed a concept called ionic product of water. Considering the first reaction, we could define ionic product of water Kw. Ionic product of water is denoted as Kw, which is equal to the product of the molar concentration of H3O plus ion and OH minus ion. That is, it is a product of hydronium ion and hydroxyl ion. And we know H3O plus ion concentration is always equal to OH minus ion concentration in case of water molecule. Or we could say the ionic product of water Kw is equal to product of H plus ion and OH minus ion. Hence, we could define ionic product of water is the molar product of the molar concentration of H plus ion and OH minus ion. At room temperature, the molar concentration of H plus ion and OH minus ion same or equal, and experimentally it is determined as 1 into 10 raised to minus moles per liter. See here, at room temperature or 25 degrees Celsius, the molar concentration of H plus ion, which is equal to molar concentration of OH minus ion, and the value is 1 into 10 raised to minus 7 moles per liter. Hence, the value of Kw is 1 into 10 raised to minus 7 multiplied by 1 into 10 raised to minus 7, that is equal to 1 into 10 raised to minus 14 moles per liter. And experimentally it is observed that the value of Kw changes with the temperature. As temperature increases, more and more water molecules decompose to form H plus and OH minus ion. Hence, the Kw value increases. So we could say ionic product of water is defined as the product of H plus ion concentration and OH minus ion concentration. Now we move to another concept, that is pH concept. What is pH? The full form of pH is power of hydrogen or potence hydrogen. Power of hydrogen or potence hydrogen, that means it gives us an idea about how much H plus ions are potentially present in a particular solution. Even though there are a large number of H plus ion, we have to consider how much H plus ion are present potentially in a particular solution. And we know H plus ion concentration is always equal to H3O plus concentration, that is hydronium ion concentration. Hence, we define pH is the negative logarithm of molar hydronium ion concentration, that is H3O plus concentration or hydrogen ion concentration. It is given as pH is equal to negative logarithm to the base 10 of H plus ion concentration. So, by calculating the H plus ion concentration, we could find out the pH of any particular solution. And pH is a measure of hydrogen ion concentration. That means if there is a large number of H plus ion concentration, the solution is acidic. And if the H plus concentration is low, it is basic or alkaline. So, by calculating the pH, we could say whether a solution is acidic or basic. If the pH is below 7, then the resulting solution is acidic. And if the pH is greater than 7, it is basic. And we know from the ionic product of water, we have seen for pure water, H plus concentration is equal to OH minus concentration. Hence, the pH of pure water is 7 because negative logarithm to the base 10 of 1 into 10 raised to minus 7 is 7. So, when we consider pure water, the pH of pure water is 7. If we add some H plus ion, the H plus ion concentration increases. As a result, the solution becomes acidic and hence the pH is less than 7. When we add OH minus ion, the OH minus ion concentration increases and as a result H plus ion concentration decreases. So, the pH of basic solution will be greater than 7 and that of acidic solution is below 7. For a neutral solution, the pH is 7. Similar to POH, we have another term called POH. pH we have defined as the negative logarithm to the base 10 of H plus ion concentration, and POH is nothing, it is the measure of negative logarithm to the base 10 of OH minus concentration. So we have to calculate the OH minus concentration in a particular solution and take its negative logarithm to the base 10. So we could define POH is the negative logarithm to the base 10 of OH minus ion concentration. And POH is used to find out the basicity of a particular solution. And POH is equal to pH for pure water, because for pure water H plus concentration is 1 into 10 raised to minus 7 and hence pH is 7. For pure water OH minus ion concentration is equal to 10 into 1 into 10 raised to minus 7 and hence the pOH is 7. So for pure water the pH and pOH are equal and it is 7. When we consider ionic product of water Kw, we know Kw is H plus into OH minus ion and the molar concentration of H plus ion is equal to the molar concentration of OH minus ion and that is equal to 1 into 10 raised to minus 7 moles per liter. So we are taking the negative logarithm to the base 10 of Kw. Negative logarithm to the base of 10 of Kw. What is Kw? Kw is the ionic product of water. And when we take the negative logarithm of Kw, we get pKw. So pKw is defined as negative logarithm to the base 10 of ionic product of value Kw. And we know the ionic product value is 1 into 10 raised to minus 14 at room temperature, because 1 into 10 raised to minus 7 multiplied by 1 into 10 raised to minus 7 is equal to 1 into 10 raised to minus 14. So Kw is 1 into 10 raised to minus 7 multiplied by 1 into 10 raised to minus 7, that is equal to 1 into 10 raised to minus 14. When we take pKw, it is a negative logarithm to the base 10 of 1 into 10 raised to minus 14, that is equal to 14. So for pure water pKw is 14. And we have seen for pure water pH is 7, pOH is 7. Hence pKw is equal to 7 plus 7, or we could say pH plus pOH is equal to 14. Are you following it? See, Kw is 1 into 10 raised to minus 7 multiplied by 1 into 10 raised to minus 7. And pKw is the negative logarithm to the base 10 of 1 into 10 raised to minus 14. And the value is 14. And we know for pure water pH is equal to pOH. Hence pH plus pOH is equal to 14. That means for a particular solution, if we know pH, then we could calculate pOH. How? pH is equal to 14 minus pOH will give you pH. Or pOH is equal to 14 minus pH. So by calculating either pH or pOH, we could find out pH and pOH of any particular solution. So we have seen pH, pOH and pKw. Now we move to certain other terms. They are Ka, pKa, Kb and pKb. And these terms are very useful to find out the strength of acids and bases. Whether an acid is strong or a base is strong, which could be easily identified by measuring Ka or pKa, Kb or pKb values. So these values are used to find out the strength of acids and bases. Ka and Kb are the dissociation constants of acids. Ka and Kb are the dissociation constants of acids and bases respectively. Listen again carefully. Ka is the dissociation constant of an acid and Kb is the dissociation constant of a base. Now see here, they describe the degree of ionization of an acid or base. Ka and pK are related to acids while Kb and pKb are related to bases. Ka is the dissociation constant of an acid and pKa is equal to negative logarithm to the base 10 of Ka. So to find out pKa, we should know Ka, the acid dissociation constant. If the acid dissociation constant Ka is known, by substituting the equation negative logarithm to the base 10 of Ka, we get pKa. Similarly, if we are able to find out the dissociation constant of a base Kb, then we could find out pKb, because pKb is equal to negative logarithm to the base 10 of Kb. So, by calculating or finding or computing or analyzing the Ka value, we could say whether the acid is strong. Kb value, we could say whether the base is strong. Or by finding out the negative logarithm of Ka or Kb value, we could find out which acid is stronger, which acid is weaker, which base is stronger, which base is weaker. So, these four values Ka, pKa, Kb and pKb are used to find out the strength of acids. Now see here, greater the value of Ka, greater the strength of the acid. When we find out the dissociation constant of an acid Ka, if the value is very high, then we could easily say the acid is very strong. That means it contains a large number of H plus ion. But if the pKa value is smaller, pKa value, see what is pKa value? Negative logarithm to the base 10 of K. If the pKa value is smaller, the acid is stronger. See, Ka and pK, greater the value of Ka, stronger the acid, and smaller the value of pK, stronger the acid. Or we could say, if the pK value is high, the acid is weaker. Clearly understand that concept. If the value of dissociation constant Ka is high, the acid is very strong. If the value of pKa is high, the acid is weaker. Similarly, a larger value of Kb indicates the base is a strong base. It contains a large number of OH minus ion. And greater the pKb value, the base will be weak, or it will be a weaker base. So, by comparing either Ka or pKa or pKb and Kb, we could find out the strength of acids and bases respectively. So, we have seen what are acids, ionic product of water, what is pH, what is pOH, what is pKw, and we have find out what are Ka and pKa, Kb and pKb, and how they are useful for predicting the strength of acids. So, my dear students, we have seen very briefly what are acids and bases and the three different concepts of acids and bases. Then we have seen the ionic product of water. What is ionic product of water and how we could calculate the ionic product of water and its value. And we have find out what is pH, pOH, pKw, and how pH and pOH and pKw are connected. Finally, we have seen what are the importance of Ka, pKa, Kb and pKb. And we have find out that Ka and pK are related as negative logarithm to the base 10 of Ka values, and Kb and pKb are related as negative logarithm to the base 10 of Kb values. And Ka and Kb will give the idea about the strength of acids, while Kb and pKb give an idea about the strength of bases. Thank you for listening me. Thank you, my dear students.